Hello students, in today's class I will discuss about the applications of Gauss law. So where we apply Gauss law? See, we use Gauss law to find the electric field due to a infinitely long straight wire. If a straight wire is uniformly charged, we can find out electric field due to infinitely long straight wire. And also we can apply this Gauss law to find the electric field due to infinite sheet. If it is uniformly charged, then we can find the electric field due to uniformly charged infinite sheet. And also we can find electric field due to thin spherical shell. So these are the three applications that we discuss in our chapter. Okay. So let me explain in detail how we use Gauss law to find the electric field due to this infinitely long straight wire and infinite sheet and also thin spherical shell. So for that first applications of Gauss law, that is we use Gauss law to find the electric field due to infinitely long straight uniformly charged wire. For that, let us consider a positively charged infinitely long straight wire which is having the linear charge density as lambda. Linear charge density as lambda, and the total charge present in this long straight wire as Q. Okay. Now, we all know electric field due to a charged conductor is always perpendicular to its surface, right? Electric field is always perpendicular or normal to the surface of a charged conductor. So, electric field due to this charged conductor is perpendicular, means normal to its surface. To find the electric field, total electric field due to this charged conductor, so we have to use Gauss law, right? In order to use Gauss law, according to Gauss law, we say the statement as the total electric flux due to imaginary closed surface is always equal to 1 by epsilon naught times the net charge enclosed by that surface. So we use we consider an imaginary closed surface and we call that imaginary closed surface at which the Gauss law can be applied as a Gaussian surface. So let us consider for this Gaussian surface as the cylindrical surface. Gaussian surface as the cylindrical surface. So here this is the cylindrical Gaussian surface. Now we need to find out the electric field. Let it be at the point P, observation point as P, and this P is at a distance R from this charged wire. By taking this distance as the radius, we are drawing this Gaussian surface. Okay. Now take a wider view of this. Here, this Gaussian surface is consisting of three surfaces. See, the cylindrical Gaussian surface will be like this. One is the circular end, and the second surface is also the circular end, and the third surface is the curved end or curved surface. So, two circular surfaces and one curved surface. So, if we consider the first circular surface, the normal drawn to this circular surface, just assume this as a circular surface, the normal should be drawn perpendicular to it, right? It will be like this. See, this is the circular surface and this is the normal. And electric field due to this charged wire is normal to this wire, right? So now see, the electric field and normal are perpendicular, therefore angle is 90 degree. So for the first circular end, so the total flux will be calculated as the flux due to the first circular end will be given by, we know from the flux definition, D delta phi 1 is equal to E delta S cos theta, right? E delta S cos theta. But here see, theta is 90 degree, right? Theta is 90 degree. If theta is 90 degree, cos 90 will be equal to 0. Cos 90 will be equal to what? 0. So cos 90 0 means this cos theta term becomes 0. 0 multiplied by anything is 0. Therefore, flux due to the first circular end is 0 because the normal and electric field are perpendicular to each other. Here theta is angle between electric field and normal. If this is 90 degree, cos 90 is 0. 0 multiplied by anything is 0. In a similar way, if we consider the second circular end, see here also electric field and normal to delta S are perpendicular to each other. Therefore, here also cos 90 is 0. 0 multiplied by anything is 0. So, similarly, flux due to the second surface is also 0. Then, so we have to find out the flux due to the third surface. So how we can find flux due to the third surface? Third surface is the curved surface, right? See, if this is the curved surface, normal for the curved surface like this. See, this is the normal, the forefinger. See, this is the normal to this curved surface. So this is the normal. See, electric field is also along the same direction. That means angle between this normal and electric field is 0 degree. So, here for the curved surface, we write theta is equal to 0 degree. If theta is 0 degree, cos 0 will be equal to 1. So therefore the total flux delta phi 3 is equal to what we can write? E delta S cos theta. So here cos theta value is 1. 1 multiplied by E into delta S gives E into delta S. Right. So therefore, the total flux due to the whole cylindrical Gaussian surface is total flux is equal to phi is equal to delta phi 1 plus flux due to first surface plus flux due to second surface plus flux due to the third surface. Right. So, flux due to the first surface and second surface is 0. So, del phi 3 value we all know that is E delta S. Therefore, 0 plus E delta S is equal to E into delta S. Here delta S is nothing but the area of this cylindrical Gaussian surface. See, consider the cylindrical Gaussian surface is of the length L. So, the area of this cylindrical Gaussian surface will be equal to 2 pi r into L. So, we write the area of the cylindrical Gaussian surface as 2 pi r, circumference into the length of the cylinder, that is 2 pi r into L, where r is the radius of the cylindrical Gaussian surface and L is the length of the cylindrical Gaussian surface. Therefore, phi is equal to E into, so delta S value is 2 pi r L. Let it be equation 1. Then, by the definition of linear charge density, we write linear charge density is the charge per unit length, right? So therefore we can write Q divided by L. In order to find out the total charge present, so enclosed by this Gaussian surface, so take this Q as it is and take this L to this side. So we can write Q is equal to lambda into L, right? So then, from Gauss Law, we can write, according to the statement of Gauss Law, the total flux passing through the Gaussian surface is equal to total charge divided by epsilon naught, right? So, total charge is nothing but lambda L. Therefore, we write lambda L by epsilon naught. Let it be equation 2. From equation 1 and 2, we can write, see, in place of phi, we can write E into 2 pi RL from equation 1. Therefore, we can write E into, in place of phi, so write the value of phi here. So, E into 2 pi RL, that is equal to lambda L divided by epsilon naught. This L and L gets cancelled, right? So now take this 2 pi r to this side. So we can write E is equal to lambda divided by 2 pi r into epsilon naught. We can write this as 2 pi epsilon naught into r. This 2 pi r comes to the denominator, 2 pi r. So the expression for electric field due to uniformly charged long straight, infinitely long straight wire is given by E is equal to lambda by 2 pi epsilon naught r. In this way, so by using the Gauss law, we can find electric field due to infinitely long straight uniformly charged wire, and the electric field due to that is given by lambda by 2 pi epsilon naught r. Okay, here lambda is the linear charge density, epsilon naught is, we all know it's the permittivity of free space, and r is the distance of the observation point, means point where we find the electric field from the charged wire. And in vector form, the same expression can be written as vector E is equal to lambda divided by 2 pi epsilon naught r into r cap, where r cap is a unit vector that is acting along the direction of the electric field. And the direction of electric field E is, direction of electric field E is acting radially outward if this charge present in the straight wire is positive, or if the linear charge density lambda is positive. If linear charge density lambda is positive, then electric field is acting radially outward. And if the linear charge density or charge present in the wire is negative, then the electric field is acting radially inward. Okay. So now let me move on to discuss about the next application, second application, that is how we can find out electric field due to an infinite sheet, thin sheet. Okay. So now, the second one, as it is, we have to find out electric field due to an infinite plane sheet using Gauss law, right? So for that, let us consider a positively charged infinite thin plane sheet. So this plane sheet is having a surface charge density as sigma. Consider sigma be the surface charge density of the plane sheet and Q be the charge enclosed by this, total charge present in this plane sheet. Okay. So due to the plane sheet, the electric field, since this is also an infinite plane sheet, electric field due to this positively charged plane sheet is radially outward. Let it be E. Now we need to find out the total electric field at the point P near this plane sheet. In order to find out the electric field at P, so let us draw a Gaussian surface on that point. So consider here also the Gaussian surface as an imaginary cylindrical surface. Now I have written the wider view of this. So here I have written the Gaussian, cylindrical Gaussian surface that is having the total area as A. So here we have considered the cylindrical Gaussian surface. It has as usual 3 surfaces, 2 circular ends and 1 curved surfaces. So now consider the first circular end. In the first circular end, if we draw a normal, it will be like this. So this is the circular end, right? This is the circular end. You have to draw normal like this. See? Normal like this. And electric field is also in the same direction since it is positively charged. Since this is positively charged, electric field is radially acting outward. So both the electric field and normal are acting in the same direction. Therefore angle between them is 0 degree. Therefore we can write the flux due to the first circular end, that is delta phi 1 is equal to E into delta S cos theta. Here theta is 0 degree. If theta is 0 degree, cos 0 degree will be equal to 1. So therefore cos theta value becomes 1. But area of this will be equal to, we have already considered area of the cylindrical surface as A. Therefore, so the total area or area of this will be equal to A. Therefore, del phi 1, I mean flux due to the first surface is E into A. Okay. In a similar way, if we consider the second circular end, so there also electric field is acting radially outward. Okay, and if we draw a normal, and that normal is also along the direction of electric field, therefore there also theta is 0 degree and cos 0 degree is 1, and area of the cylindrical surface is A. Therefore del phi 2 will also be equal to E into A in a similar way. Okay, now we have to find out the flux due to the curved surface. Here, flux due to the curved surface, see the curved surface will be like this. If we draw a normal for this curved surface, it will be like this. See the direction of forefinger. Okay, but electric field will be like this. Means like this. This is the direction of electric field. Either this or this. This is the direction of normal. So, here this normal makes an angle 90 degree with this electric field. Therefore, for the curved surface, I mean for the third surface, theta is 90 degree. Therefore, cos 90 will be equal to 0. If cos 90 degree is 0, then the total flux through that curved surface is del phi 3 is equal to E into delta S cos 90. I mean cos theta. Cos 90 value is 0, right? 0 multiplied by anything is 0. Here area is A. So, EA into 0 will be equal to 0. Therefore, total flux will be equal to 0. Then, we can calculate total flux due to the third surface is 0. So, the total flux due to the whole Gaussian surface, I mean whole infinite plane sheet is given by phi is equal to del phi 1 plus del phi 2 plus del phi 3. Here, del phi 3 value is 0. Del phi 1 value is E into A plus del phi 2 value is also E into A. So, this value is 0. So, we get phi is equal to 2 into EA. Okay, let it be equation 1. Then from the definition of surface charge density, we can write surface charge density is the charge per unit area. So, we can write charge by area. We need, in order to apply Gauss law, we need to find the total charge. So, the total charge Q is given by, now take this A to this side. So, A can be written as, this Q can be written as sigma into A. Okay. So, according to Gauss law, we know the total flux passing through the closed surface or Gaussian surface is the 1 by epsilon naught times the net charge enclosed. Here the net charge is sigma A. So, sigma A divided by epsilon naught. Let it be equation 2. Now, we know from equation 1 phi value, that is 2EA. Substitute the value of phi in this equation 2. So, 2EA is equal to sigma A divided by epsilon naught. See, sigma A divided by epsilon naught. In place of phi, I have written 2EA. This A and A gets cancelled. Actually, we need to find out electric field, right? Now take 2 to this side, it will comes to the denominator. So, we write the electric field due to infinite plane sheet is given by E is equal to sigma divided by 2 epsilon naught. This is the electric field due to infinite plane sheet by using Gauss law. Here we are applying Gauss law. That is given by E is equal to sigma by 2 into epsilon naught, where sigma is the surface charge density of the plane sheet and epsilon naught is the permittivity of free space. In vector form, we write the same expression as vector E is equal to sigma by 2 epsilon naught into n cap, where n cap is the unit vector that is acting along the direction of this electric field. And so this electric field due to the infinite plane sheet is acting radially outward if the surface charge density is positive, means charge is positive. And if the surface charge density is negative, then this electric field is acting radially inward. And the electric field due to infinite plane sheet doesn't depending on the distance. See, here we are not having any term related to the distance, right? So we can say electric field due to an infinite plane sheet does not depend on the distance. Okay, so this is the second application. Now we have to discuss about the third application, that is how we can find out the electric field due to a thin spherical shell. Okay, let me move on to discuss about that. Now let us consider a thin spherical shell having radius r. Consider a thin spherical shell having radius r, which is positively charged. And here O is the center of that spherical shell. Now we need to find out, here the two cases arises. If we consider a sphere, we can find the electric field outside the sphere also. If we consider any point outside, if this is the sphere, if we consider any point outside the sphere, what is the field due to that point? And also what is the field inside the spherical shell? So there are two cases in this. So first case is how we can find out electric field outside the shell. For that, so if this is the spherical shell, consider a point P outside this shell. Okay. So then, if we draw a normal, in order to find out the electric field due to this, we have to draw a Gaussian surface first. Let us consider an imaginary Gaussian surface around the point P as a spherical surface having radius small r. Here small r is the radius of the Gaussian surface, spherical Gaussian surface. Now around the point P we have drawn a imaginary Gaussian surface. So then if we draw a normal at the point P, the normal in the case of a sphere, normal should be drawn along the radius to that point. So here this is the direction of the normal. And electric field due to a spherical charged shell is, we all know the sphere, if we treat the sphere as a point charge, due to that charge electric field lines are acting radially outward. So therefore due to the sphere electric field is also acting radially outward, that is in the same direction as that of the normal. Okay. Since electric field and normal are acting in the same direction, angle between them is 0 degree. Angle between electric field and normal is 0 degree. Therefore, cos 0 degree will be equal to 1. So, the total electric flux due to the spherical Gaussian surface is given by delta phi is equal to E into delta S cos theta. Here cos theta value is 1. Therefore, we can write delta phi is equal to E into delta S. In order to find out the total flux, so now the total flux phi is equal to summation of the flux due to small elements. Here we have considered a small circular element. So total flux is sum of all those elements in that surface. So therefore phi total flux is equal to summation of delta phi becomes summation of E into delta S, that is, now take E to outside, so E into summation of delta S. Sum of all the smaller area elements is equal to total area of the spherical Gaussian surface. So area of a sphere is known to us, that is 4 pi r square, right? So area of a spherical Gaussian surface is nothing but, so here we write E into area of the sphere is, our spherical Gaussian surface is 4 pi r square. Okay. Therefore, we write E into 4 pi r square. Let it be equation 1. E into 4 pi r square. In the same way, now, so find out, in order to use or apply Gauss law, so according to Gauss law, total flux is the 1 by epsilon naught times the net charge enclosed. First, we have to find out the net charge. So now consider this actual sphere is having the radius r. Therefore, area of this spherical shell is 4 pi r square. Area of the spherical shell is 4 pi r. Now I am concentrating on this sphere only. Okay. So not on the Gaussian surface. So therefore, area of the spherical shell is 4 pi r square. Let us consider surface charge density of the spherical surface as sigma. Surface charge density as sigma. Okay. Therefore, so from the definition of surface charge density, we can write sigma surface charge density is equal to charge per unit area. So charge by area of the sphere is 4 pi r square. Okay. So now the total charge is given by Q is equal to sigma into 4 pi r square. According to Gauss law, the total flux is given by phi is equal to Q divided by epsilon. We already found the Q value, total charge value. Therefore, we can write Q in place of Q sigma into 4 pi r square divided by epsilon naught. Let us take this as equation 2. From equation 1, we know the value of phi, that is E into 4 pi r square. Now substitute here. So E into 4 pi r square can be written as E into 4 pi r square. See, in place of phi, we have written the value of phi is equal to sigma into 4 pi r square divided by epsilon. This 4 pi and 4 pi gets cancelled. Therefore, we write the electric field due to a thin spherical shell or a spherical shell is given by E is equal to. Now take r square to this side, it will comes to the denominator. Therefore, E is equal to sigma r square in the numerator. Then epsilon naught small r square is in the denominator. This is the expression for electric field at any point outside the spherical shell. At any point outside the spherical shell. That is E is equal to sigma into r square divided by epsilon naught into r square. Okay. Now, so what is the electric field at any point inside the spherical shell? For that, let us consider again the same spherical shell. Here, I have considered the spherical shell which is having a surface charge density as sigma and it is positively charged and O is the center of the spherical shell. Now consider the Gaussian surface inside the spherical surface. Means we have to find out the field, electric field at any point inside the shell, right? Inside the shell. Therefore, we have considered the observation point P inside this spherical shell. So, around this observation point, we have written a Gaussian surface which is having the radius R. And the sphere is having the radius capital R. Okay. Now, so the flux due to this Gaussian surface is given by, from equation 1. See here, nothing has been changed. Sigma is as it is. Q is as it is, right? So, electric field is also as it is. Only the thing is, this R, distance of the Gaussian surface is reduced. Let it be R only. Therefore, so by referring equation 1, so we write flux due to this Gaussian surface as E into 4 pi R square. Okay. Now, in order to apply Gauss law, let us consider the flux due to, so this spherical shell, so at any point inside is given by, so net charge enclosed by that surface divided by epsilon naught. See, inside this Gaussian surface there is no charge. In the case of conductors, we know charges always resides on the outer surface. So inside the sphere there is no charge. That means the charge enclosed is 0. Q is 0. 0 by anything is 0. Right. So the flux is 0. If flux is 0, so we write F phi is equal to 0. That is equal to phi value is E into 4 pi r square. Now take this 4 pi r square also into this side. So 0 by anything is 0. Therefore electric field inside the spherical shell is 0. Okay. So electric field, so inside the shell is 0 and electric field outside the shell is given by the previous expression that I have written. Okay, so this is about the electric field, so due to a spherical shell. So then now, so let me move on to discuss about the next concept, that is electric field at any point outside the shell is derived in the previous section, right? That is given by sigma into r square divided by epsilon naught into small r square, right? So now, in place of sigma, we know sigma is nothing but charge per unit area, and area of the spherical shell is already known to us, that is q by 4 by r square. Okay, we have derived. Now substitute this value in this equation. So we can write in place of E, in place of sigma, q by 4 pi r square into r square divided by epsilon naught into small r square. This r square and r square gets cancelled. So we write, now this 4 pi goes to the denominator. Therefore we write q by 4 pi epsilon naught r square. And we can write this as individually 1 by 4 pi epsilon naught into q by r square. So this is the another form of the expression for electric field at any point outside the spherical shell. Okay. So this completes the theory of the first chapter, that is electric charges and fields, and in the next class I will continue with the problems. Okay, thank you.